I add you as a co-host. And we can wait a couple of minutes, then we can start.
Yeah, sure.
Well, I think we can start. So good afternoon, everyone, and welcome to our IPARCOS seminar. Today, we have the pleasure to have with us Felix Priestley from the Cardiff University in UK. Felix received his PhD in astrophysics from the University College of London in 2018 under the supervision of Professor Mike Barlow. His PhD thesis was titled Molecule and Dust Emission at the Beginning and End of Stellar Evolution, awarded in December 2018. After his PhD, he was a postdoctoral research associate at the University College of London. His research interests are mainly focused on the gas dynamics and chemistry in star-forming regions and the formation and evolution of cosmic dust. Today, Felix will present his work titled Testing Theories of Star Formation with Molecular Line Data. So thank you very much, Felix. The floor is yours.
Right, thank you for inviting me in the introduction. So, as was explained, I'm basically going to be focusing on some stuff I've been doing over the last few years at Cardiff, which is focused on actually testing all the theories of star formation, which I'm meant to be working on most of the time. So there's a list here of people who have been involved with various bits and pieces of this. Hopefully I haven't missed anything, but views presented are all my own, so I'm not sure they necessarily agree with everything I say, but they've been very helpful. So anyway, so star formation is possibly, from my biased point of view, is the kind of one of the most fundamental bits of astrophysics research, because it kind of glues everything together from galaxy scales down to planets and stuff. So unless you're kind of working on large scale CMB observations or something, at some point you're probably going to have to worry about how stars form and how they do it. So it is obviously very important in controlling how you re-inject sort of energy and nuclear processed material back into the interstellar medium. So that's obviously very significant for simulations of galaxy evolution and stuff, and the general interstellar medium. The details of that process, so the initial mass function of stars and the efficiency of converting gas into star formation will, depending on that, could completely change how your galaxy and, you know, cosmological volume or whatever is actually evolving. And on the much smaller scales, of course, planets form around stars. I guess you could possibly have free floating planets as well, but at least most of the ones we know about are located around stars. They presumably form at about the same time, and basically as a side effect of the main process of star formation. And there's a significant amount of research going on into the fact that a lot of these sort of protostellar, protoplanetary systems have very rich sort of chemistry, making it of, you know, going up to, I think, the amino acid levels. So the potential implications for whether you can deliver that stuff onto planets and maybe give biology a kickstart, essentially, is becoming, well, I think it was, you know, back in the 50s, people probably thought that was a totally crackpot idea, but now it's actually being taken seriously, which I think with quite good reason. So in some sense, we actually understand star formation pretty well in a very sort of broad strokes way. You have cold gas, gravity makes it collapse because it can overcome its internal pressure, and the kind of general turbulent motions in it will give you the structures that we see in molecular clouds. So here are some observational images by Michael Anderson's paper. He's a PhD student at Cardiff. He makes quite nice plots, so I tend to steal them for talks. So the upper two panels of I think this is Spitzer 8 micron mid-infrared images of 2 bits of the galactic plane. So there's a kind of background emission with some point sources in it. And superimposed on that, you can see absorption, where you've essentially got a lot of very cold, very dense gas and dust in a so-called infrared dark cloud, which is, as you can see, kind of vaguely filamentary in structure. You've got long, thin bits which kind of merge with each other into local densities. The bottom 2 panels are, I think this is ALMA data from 3 millimeter. I'll have to double check with them about that. But anyway, so far infrared, sort of sub-millimeter level, tracing the sort of densest, coldest bits of the thing by the thermal dust emission. So compared to the kind of larger scale filamentary structures, you basically mostly just see a couple of blobs here, which are the kind of absolute densest bits, which are actively collapsing and forming stars. So you can hopefully see that some of these blobs correspond to mid-infrared bright patches on the top panels, which kind of suggests that you've actually already formed a protostar, which is heating up the dust around it, whereas some other ones don't and have basically just blank in the mid-infrared bit, which are generally the so-called prestellar cores, which haven't yet formed anything but are likely to do so at some point in the next million years or so, which are generally the ones I focus on because it's much easier if you don't have a star there messing everything up. So that's the kind of nice sort of overall picture of what's going on, but the details are much less certain. So there's I think known since the 70s, the fact that the efficiency of this process converting stuff into stars is very low, sort of the order of a few percent, at least, of a sort of a free-fall timescale. And there have been plenty of suggestions of why this is, but it's not actually clear which ones apply. So I think the current most popular one is that the feedback from the stars disrupts the cloud itself. This is reasonable enough, but if you look at the actual models that go into it, there's a lot of moving parts, which always makes me slightly suspicious of how nicely everything works out in the end. Again, the actual timescale over the process of which you assemble this cold gas in the first place and how that happens is not completely clear. Again, people have tons of different theories about how it might happen with cloud collisions, galactic dynamics, and so on. But it's not necessarily established which of these apply to the real objects we see, which are actually forming stars in the Milky Way. And the kind of fundamental problem of this, which is what I'm going to spend the rest of the time trying to get around, is that observationally, you can only see 2 dimensions projected on the plane of the sky, and you have 1 velocity dimension on the line of sight. This is only really true of sort of emission studies of dust continuum and molecular line emission. Thanks to Gaia, I think there's been some recent things of kind of tracing the 3-dimensional structure using the distances to stars and protostars. I think there's an ongoing project by, I think I've forgotten who's doing it now. I remember seeing them talking about a conference of actually getting this full 6-dimensional information, again, using distances from Gaia, very detailed sort of proper motion studies. But by and large, almost all observational studies of molecular clouds and star-forming regions, you have 2 spatial dimensions, and if you're lucky, 1 velocity thing. So this is a kind of good example of the issues with this, with a recent paper by Aris Tritsis and people. So that's nice image is the column density image of the Musca molecular cloud, which again looks very nice and filamentary. But I've only discovered this when I saw the paper pop up in the archive, but there seems to be an ongoing discussion about whether it's actually a filament or whether you're looking at a kind of sheet-like structure in the plane of the sky, edge on. So obviously the interpretation of what you're looking at in those 2 cases would be completely different, especially because if it's a sheet, the average density is much lower, which changes your interpretation of the average star formation rate in the cloud and so on. And basically we just don't know. So they make a lot of arguments in the paper, which kind of supports their interpretation of sheet rather than filament, but there's no definitive way of doing this, and it's basically just fundamentally not knowable because we can't see the 3D structure. So this is not even testing a theory, basically. This is just pointing out that we can't even actually tell what we're looking at some of the times in some sense. When you get into the kind of detailed differences between what different theoretical models predict, which is generally, you know, the 3-dimensional density structure, the 3-dimensional velocity, and most of that, so over half of that information basically just can't be measured, full stop. And the stuff that can be measured is only in a very roundabout way. So at the temperatures of molecular gas, hydrogen doesn't emit at all. So you can only measure the column density along the line of sight by proxies such as dust, which is probably quite reasonable. But again, there are likely to be systematic effects which throw that off. The velocity is an even worse case because you're basically trying to get that out of a line profile from usually some molecular line emission. And as I'll come to later in the talk, it's quite suspect exactly whether these things correlate even in the slightest. So trying to extract quantities you could use to test theories of star formation from data is really not trivial and sometimes actually impossible. So my kind of interest of this started with my undergraduate project at University College London with Serena Vitti, where the idea was basically to take different models proposed in the literature for the collapse of a prestellar core. Again, this is one that doesn't have a star in it, which makes it much simpler to model. And basically follow the chemical evolution of these things and see if there are any noticeable differences, basically, because there were loads, I mean, I think we're in the hundreds now of detected molecules in space, most of which are found in molecular clouds, but as the name would suggest. A lot of these are quite sort of, you really have to go looking for them. But there was still sort of a solid dozen or so molecular species with quite bright lines that you can basically pick up just by getting any old millimeter telescope, pointing at a cloud for a bit, and you'll get sort of 5 or 6 lines. Each of these lines is potentially a completely different independent test, essentially, because the chemical difference of chemical behavior of different molecules is different, quite often quite sensitive to the evolutionary history. So there's a lot of quite potentially useful data lying about. And the idea behind this was, can you exploit it into, actually distinguishing between models? So the biggest difference we found on the left panel, this is just the CO radial abundance profiles for 2 models as an example. CO is the most abundant molecule and basically the one you really want to nail down if you're going to do anything else useful. So the distinction between the 2 lines here are 2 different models which are identical except for the magnetic field strength. So the terminology is unfortunately quite confusing. Basically, the key quantity for determining the balance between gravity and magnetic support is the mass to flux ratio. If you have a mass to flux ratio above the critical value, it's known as supercritical, and basically the field can't stop collapse, and you more or less have the core collapsing on a free fall time. If it's below the critical value, then it takes much longer because you have to basically wait for lose magnetic support over sort of timescales, which are typically at least a factor of 10 longer. Which is the so-called subcritical case. So we found this is basically the biggest difference with models, which actually affects the chemistry, basically because of this much longer evolutionary timescale. So the orange line, the supercritical one, you can see has a basically standard, what you'd expect behavior. So at the outer radii, the CO abundance is basically equal to the atomic abundance of carbon. So all of the carbon has been locked up into the molecule, which then declines as you go into the denser inner bits because the gas phase molecules start freezing out onto grain surfaces. The subcritical model does the same thing, but to a much greater extent, basically because it spent much longer at higher densities because of the additional magnetic support. So this is a kind of gigantic 2 orders of magnitude difference throughout most of the volume of the core in the abundance of the most commonly detected, most easily detected molecule. Unfortunately, this turned out to be much less useful than I was hoping because, again, you can't detect the volume abundance. You can only detect it projected on the plane of the sky, which gives you the ratio of column density of carbon monoxide or whatever other molecule to the total column density of hydrogen. When you do this, the difference basically disappears because you always essentially have this high abundance stuff in the outer regions of the cores, which makes up a significant amount of mass. So this gigantic drop in the volume density profile isn't apparent at all in the thing that you can actually see and measure. And the difference between the models has gone down to basically a factor of a few. And given the large uncertainties in estimating the molecular abundance in the first place, and then the amount of hydrogen along the line of sight as well, I don't think that's ever going to be trustworthy in terms of measurement, particularly when you add in the model uncertainties as well. So this was quite disappointing, basically. I did spend quite a lot of time in the 2019 paper trying to find cases where we might be able to distinguish between the 2 cases, or indeed any other case. I don't really find much of it that convincing in hindsight. So what I moved on to was instead looking at line observations instead, so that rather than trying to derive molecular abundances from lines, just see what does the model predict for the line anyway. So the fundamental way this works is that, so you take your hydrodynamical simulation of a molecular cloud or a core or whatever. So on the left panel is the surface density or column density of just a standard sort of turbulent ball of gas that you let collapse over the course of about a megayear or so. So it forms these filamentary structures with the kind of high density hubs that you see in the data. You follow the chemical evolution of this model. I use smooth particle hydrodynamic simulations because it makes this almost trivial in a sense, because you have your individual gas particles. You can just take the time evolution of their density, plug it into your chemical, time-dependent chemical network, and you get the abundance out as all over time. And then you can use the positions of your particles to build up the three-dimensional molecular structure of the cloud as predicted by the simulation. You can then plug that into radiative transfer code. I tend to use Line because it was the first one that popped up in 3D basically, but it doesn't really matter which one. And this combination of the hydrodynamics and chemistry gives you all the information you need to produce what are basically self-consistent line observations. So position, velocity cubes of the intensity in whatever transition from whatever species you want. So on the right panel is the result of that for the 13CO 1 to 0 transition for the same cloud for some stuff I was doing most of last year, and the paper came out a few months ago. So you can see that the basic shape of the cloud is the same as the underlying density and the CO, but because the molecular, basically the line becomes optically thick at quite a low surface density, so you lose all the contrast between the dense structures and the diffuse underlying gas and just end up with this quite amorphous blob, basically. So not the best way of checking what's going on. The underlying motivation for these simulations, in fact, was a paper a few years ago by Tafaya et al., which observationally went and looked at the Perseus molecular cloud and found this incredibly regular behavior between the intensity of lines, CO included, but pretty much everything else they looked at as well. So again, the kind of dozen or so relatively easy to detect simple molecules, and the surface density of the gas as measured by dust extinction, which is not quite the same thing, but I think probably good to within a factor of a few. So the fact, these are the black circles in this line. So the fact, this plot, sorry, so these are the surface density of the gas versus the line intensity of various transitions. The black circles are the data from Perseus, which you can hopefully see if you ignore all the other symbols. They're very regular and basically have a one-to-one correlation with the actual shape of that relationship being different for different lines. So when I saw the observational data for this, I thought, well, that's incredibly neat, and I'm sure that that cannot possibly come out of the messy sort of hydrodynamical chemical simulations, but to my great surprise, it actually kind of did. So the colored points here are the from the previous simulation on the slide before. So I've just taken basically, you know, for each pixel you have a value of the surface density, you have a value of the intensity in whatever line. So you stick them all together, take the average. The different colors here correspond to looking at the cloud from different angles, which for a initially spherical ball of gas should be statistically identical, and in fact are, which is nice. So I'd be very worried if it wasn't. And you can see that basically with very little fiddling at all, I had to come up with an equation, a somewhat realistic equation of state, but there was no attempt to kind of force the models to fit the data here. I was actually hoping that they'd rule out the models. And you end up with pretty much exactly what you see. So the CO line, again, as observed, it kind of pops up, the intensity goes up quite rapidly. The more gas you have up until the point where the line gets optically thick, and then it basically just flatlines. You don't get any more emission by having more stuff. HCN has an almost exactly linear trend. So the more stuff you have, the more emission you have in pretty much the same proportion. That again comes out of the model. There's a slight offset there between the intensities predicted by the model and the ones observed, which is mostly down to the fact we neglected the hyperfine structure of the line, basically because it would involve years of calculation time if we had to do that properly. N2H plus, which again is probably the only thing that could actually be described as a dense gas tracer, because rather than this nice linear correlation here, you essentially have no emission detected at all up until the column density of about a few hundred solar masses per parsec squared. then it goes up as a kind of, again, roughly a linear slope, I think it was, between the amount of stuff and the amount of line. And again, this happens in the models with basically no fiddling at all. It's just a natural consequence of the chemistry of the molecule and how it interacts with the dynamics of the cloud. So that was, again, your kind of bog standard sphere of gas with some initial turbulent motion in it. And it seems to work much better than I could possibly expect as a representation of real molecular clouds. Again, this is only data from one, but there have been other studies on other clouds which find similar, if not necessarily identical, relationships. So these basically, despite the fact that these objects are definitely not spheres of gas with an ordered turbulent field in it, it does seem to capture a lot of the underlying physics that's going on, which suggests that you can, in fact, get away with making all these simplifications to the model and still have something that's basically realistic. This isn't always the case. So we tried a bunch of different cloud models in the paper. Popular one that you see quite a lot of people proposing either in their simulations or as something they've detected observationally is collisions between two molecular clouds, which can kind of generate quite rapidly a bunch of dense gas, which you would expect to form stars. So this results in quite different behavior for the predicted line emission out of the model, particularly focusing on CN. So instead of this nice linear relationship where you get more emission, the more stuff you have, at some point around, again, a surface density of a few hundred solar masses per parsec squared, it just cuts off and flatlights. So much like the CO line, you no longer increase the emission the more stuff you get. Happens to a lesser extent in N2H+ as well, but there's some caveats there related to the hyperfine structure, so don't hold too much faith in that. But so this looks like an optical depth effect, like it is with CO, but it turns out not actually to be the case. These lines are basically optically thick always, and well, I'm not completely convinced, but the best explanation we could come up with why you get this almost perfectly linear relationship is that the velocity dispersion of the gas tends to go up as you increase the surface density. Basically, you have more stuff and it tends to be moving at different velocities. So in the turbulent case, that again, somehow, very surprisingly, works out as an almost exactly linear rise in the density with surface density. The colliding case, basically because at high densities, you've squashed all your gas together and dissipated a lot of the initial velocity. So you basically run out of bandwidth for the line and you can't produce more emission by having more stuff just because it's optically thick. It just gets trapped and nothing happens, basically. So speaking of line widths, I did mention before that you measure these, measure gas velocity, or at least the line of sight velocity observationally from line widths. Not line width, sorry, but from the information in the spectral lines. And at least in the models, it's not clear that this works particularly well. So the left panel here shows the velocity dispersion of the gas. The black points are weighted by the mass. The red ones are weighted by the volume. The reason we tried both was because if the lines are optically thick, at some point, the relevant quantity for predicting the actual emission switches between having more stuff and having more stuff in space with different velocities. Probably not, that's not a brilliant explanation, but I really can't think of a better way to put it. So you can see, again, this is for the bog standard ball of gas with a turbulent field in it, which then collapses under gravity. You have this quite sort of ordered rise where, as you increase the amount of stuff along the line of sight, you have an increase in the velocity dispersion. At some point, if you weight it by mass, this goes down again because the densest parts of the cloud, most of the mass is concentrated in these very dense structures, which are being gravitationally bound and collapsing. And they've, again, dissipated a lot of their initial turbulent motions. So the average dispersion on the line side drops, whereas if you do it by just weighting each bit of stuff equally, essentially, rather than by mass, it flatlines at some constant value. So you would expect, or hope at least, if your molecular lines were actually tracing the gas motions quite well, that you would see something similar to this in the line widths, but you don't, essentially. So this is the 13CO line width. again, measured as a function of surface density. It's not exactly equivalent to the velocity dispersion, but it's there's the conversion between them isn't massively affect these results. So you might, if you squint, be able to see some kind of evidence of a rise going on with surface density there, but it's not immediately clear that this is actually happening. It's worth noting that the scales here are different, so that your velocity dispersion at low column density, for example, of the line isn't actually representing the dispersion of the gas. And you don't see this drop. It's basically just turns into a mess there because we're dealing with low number statistics. But the gas dynamics, even for the one dimension of velocity, you can actually observationally trace, seems to have very little relation to the observational signatures that are used to trace it. We haven't explored this massively at the moment. It's definitely on the thing, but it is, again, another sign of trying to extract theoretical quantities from observations is a lot harder and a lot trickier than predicting the observational ones from the theory, which you can then just go and, again, pretty much overplot data and see what it does. How am I doing for time? Not bad. Okay, so that was molecular clouds. Again, to my great surprise and disappointment, it turns out the simplified models everyone uses actually work quite well. I'm never really a fan of making theorists happy because they're always gloat for ages. So moving on to smaller scale structures, and back where I started basically on prestellar cores. So so the left plot is the one I was showing earlier. So there's this kind of two different regimes of magnetic support. You have the supercritical case where the field can't prevent collapse and everything happens very similarly to the case with no magnetic field. You have the subcritical case where the magnetic field can delay gravity for anything up to a megayear, depending on the initial conditions, compared to typically sort of about a tenth of that for the unimpeded freefall collapse timescale. So again, the magnetically supported models have very different abundance structure due to the longer collapse duration, which isn't actually apparent in the observable column densities. But I did wonder what would happen to the line. Basically, looking at lines rather than column densities gives you the extra dimension of velocity, which might let you sort of peer into the center, which is obscured by line of sight effects otherwise. So this was work by Charles Yin a few years ago, who did his MSc undergraduate project with me in Cardiff. Almost entirely over lockdown, which made it even more impressive. He managed to dig out so much stuff out of this. So he basically took these models that I'd run a few years before and chucked the radiative transfer model at them to see what they'd actually look like. So I wasn't massively, given the disappointment of the column density results earlier, I wasn't enormously enthusiastic about the prospects of this. But to his great credit, he managed to pull out something much more interesting than I would have done. So specifically, so the right panel here is the results from his work, where you have the CS 2-to-1 line profile. This is chemically quite similar to CO in that it depletes quite effectively at high density, and you get this big distinction between the two models. But because there's a lot less CS than there is CO, the lines are less optically thick, and you can see differences between the two models much more easily. So your orange supercritical profile is, as you can hopefully notice, much stronger than the subcritical one, basically because there's this huge difference in the abundances. So you have more stuff, it emits much more. You also, because you have more stuff along the line of sight, you have a much stronger self-absorption feature in the line profile, which is this big dip towards the red part of the profile. And because the magnetic fields in the supercritical case aren't impeding collapse, then you have much broader lines, basically, because stuff is moving much faster. So that was interesting enough, but then I got Charles to stick some actual observational data with it, which is from L1498 here. And it turns out that the supercritical model looks absolutely nothing like any observed core, basically. The lines are just way too strong, way too broad, way too strongly self-absorbed. And the magnetically regulated ones look quite good in comparison. Again, we didn't fiddle with these to try and get it to fit the data. This is just slapping the data on top of our model once we already run it. So last year I went and dug a bit further into this because we just had one model core with two field strengths. It could just be a random effect basically, but it turns out to be pretty consistent. So supercritical cores, and I think it's worth pointing out, these are ones everyone uses in theory. The subcritical magnetically supported model basically fell out of fashion in the sort of mid-90s, and everyone has pretty much ignored it since. So the entire literature is based around these models with relatively weak magnetic fields, and they don't work at all. They look absolutely nothing like real cores. So the plots here, so on the left, Charles basically came up with this diagnostic ratio based on the single model we had before, which is the peak intensity of the CS 2:1 line versus the peak intensity of the N2H plus line, basically because CS depletes quite effectively. So it's very sensitive to the basically the time scale and more obliquely to the magnetic field strength, whereas N2H plus basically has a constant abundance whatever you do to it, more or less. So it's much less affected by the details of the evolution and acts as a kind of baseline tracer, which should be the same whatever you do. So the different colored symbols here are a bunch of different models I ran, so with different masses, sizes, densities, ages, viewing angles compared to the field axis. And the black points are a sample of data I scraped out of the literature. I would have liked to do it properly and actually get some telescope data, but I realized that I am not qualified to deal with telescope data. So avoided that for now. That's definitely something on the to-do list. So you can hopefully see that the colored points basically strategically avoid the points where all the real cores live in this kind of peak intensity space, apart from these three, which are weird for other reasons and still don't actually match the predicted N2H plus intensities. This is basically because they evolve too fast. They don't deplete enough CS, so the line strengths are too big. The line widths on the right panel are even worse. So this small box there, basically all the real cores live in that. We only had 5 data points with measurements of both lines, but if you just look at the data for the other ones, they all live around there. And basically every single model with a supercritical field strength is outside that box, massively, extremely supersonic line widths, which are basically never seen in nature. The subcritical ones do much better again than I reasonably expected. So this is the same plot as last time, the same set of models, except with the magnetic field increased by a factor of, I think, 10 in all cases. I can't remember off the top of my head. So you still get some models which look rubbish, basically, compared to the data, but you do get a significant proportion of them, again, just with arbitrarily picking a bunch of masses and sizes and whatever out of a hat, really. And they do just naturally fall pretty much bang on where all the observational data is. Line widths, again, are in the right ballpark. We've only got 5 data points, as I said, but that entire figure is the size of that small box there. So there's a serious distinction here, and it's pretty clear which ones of the models are working better. So the argument in this paper, let me just, how much longer have I got? The argument in that paper last year, obviously, was that these are the correct models, previous ones are wrong, and everyone has spent the last 20 years massively underestimating the importance of magnetic fields. Within about, I don't know, about 3 or 4 months, I think, of that paper coming out, I then discovered, to my unpleasant surprise, that these models basically can't be used to predict anything. So again, these are all models of just, you start off with a sphere of gas and let it collapse. The only difference between the cloud ones is it's much smaller scale and there's no initial turbulence in it. So this is, again, a paper that came out in November, I think, which was started off as just a kind of quick project based on some work that Erica Fogarty did way back in 2014, I think, showing that if you start off with your spherical isolated prestellar core and you change the background density, which is a kind of almost a numerical artifact, you need to have some kind of confining pressure to keep the core from confined, basically. And you're free to pick what density and temperature that background medium has, as long as the product of them, so the actual pressure, stays the same. So the red and blue, it turns out that this has some effects on the evolution of the core. So in this, the left figure shows the evolution of the central density of models. So the solid lines initially out of equilibrium, in equilibrium with, so the gravity is balanced by the thermal pressure and they're more or less static, but on the boundary of being unstable. The dashed lines are one where you increase the mass a bit, so gravity wins everywhere and the core just collapses instantly. So you can basically see, again, dashed lines where they're unstable, it just shoots up in more or less a freefall time. And at that point, you form a star at the center, basically, and we stop the simulation. The other ones sort of have this wobble basically first, which is an effect of a kind of pressure wave from the surrounding medium sort of disturbing it, which can eventually kicks the core out of equilibrium and it eventually collapses. The difference between the red and blue lines is these are identical models, except for the fact that we changed the background density by a factor of 10, which again is something that is basically usually considered as just a numerical construct to stop your core from expanding unphysically. And this has an enormous difference in the evolution. I mean, it's kind of basically a bigger effect than the difference between in or out of equilibrium in some senses. It turns out, which is what Erica's paper was pointing out, that by the time you get to this point, when you're forming a star, these differences have washed out basically, and the density profiles are completely indistinguishable. And the idea behind this paper was to see, okay, the density might be identical, but the histories are different. Chemical abundances generally remember the history. So does that have an effect? The answer is yes, and a disturbingly large effect, I think. So the right profile is the CS2-19 we were using in the previous one to diagnose magnetic fields. It turns out that whether a model starts off in equilibrium or not has pretty much no effect on the line emission, which is already quite surprising. And again, the disturbing part is that what does have a huge effect is what background density you embed the core in. So the factor of kind of 2 difference in line intensity here is effectively the same as the difference in peak intensity between the 2 magnetic fields. So again, we had to referee didn't quite understand the point of our paper at first, I think, in that he thought we were trying to argue for one case rather than another. But the argument we're pointing out here is that if the predictions from your model depend that sensitively on a parameter you basically have no constraints on and don't even consider part of the physical model, then the model can't predict anything. And you can't really trust any of these results. So feel free to ignore everything I said about magnetic fields earlier. I won't blame you. So obviously that's quite disappointing. What I'm currently working on and hoping might be a consistent solution to both of these issues is that obviously you shouldn't model cores as isolated objects because they're not. They form out of large-scale turbulent motions in molecular clouds, and this is clearly going to give you a different result than if you started off with a ball of gas sitting there. So a few years ago, me and Ant Whitworth came up with a model of filament formation in turbulent converging flows, basically because we realized it would give you reproduce the distribution of filament widths that people have spent lots of time in the literature arguing about. So a paper I actually submitted earlier today, so pretty much hot off, not even on the press actually, was doing the same thing to these models basically. So starting off with your model of a filament, running it through the chemistry and radiative transfer and seeing what would this look like. So left panel is the velocity profile, the radial velocity profile of one of these models. So you start off with this kind of very sort of supersonic, I think this is a Mach 4 number. The different line styles here are just different times. So you have your inflow coming in from both sides, and then you hit the central bit of the model, basically the flow all runs into itself. You have a very sharp accretion shock where the ambient material is slowing down quite rapidly and being converted into much denser gas at the center of the filament, which then has this slight gravitational contraction as the stuff that you've accreted onto the filament basically starts contracting. So interestingly, when we bunged that through all the chemical and radiative transfer things, the line profiles did not show any evidence basically of these supersonic motions. So the blue line there is 13CO, and you can kind of just about see that you have these kind of wings on the line profile which correspond to the accreting material. The orange line is HCN, the green one is N2H+, and in those cases it's really not very distinct. You can't actually see the supersonic bits of the cloud. All you detect with these very sort of low and in fact completely consistent with observation, the subsonic line profiles, is the bit in the middle, which has already been compressed and accreted and basically lost most of its initial turbulent motion. So the prospective idea here is that this is a way to get around the fact that your individual core models are fundamentally unpredictive and that your observed cores don't look like what you would predict based on the typical simulation thing, that you're actually forming these things out of bashing stuff together, making it have fundamentally different properties essentially to the kind of isolated models that people have spent all of their time in the literature running over. And I've pretty much run out of time, which is good because it was the last slide. So as a kind of summary of what I've been rambling on about for the last 40 minutes, it's very difficult to test simulations of theories of star formation because the quantities that come out of the models have very little relation, or at least very complicated relationships, to the things you can actually observe. And trying to go backwards from your observed stuff to what underlying density structure or whatever is producing this is very difficult, and in some cases actually impossible. It's relatively easy to go in the other direction basically and take your model and say, okay, what would this look like if I pointed a telescope at it? If you do that, then your nice simple model of a spherical turbulent cloud seems to actually agree quite well with observations, which suggests that these models are actually physically capturing what's going on, because it's, again, really not trivial to end up with this kind of linear relationship between line intensity and density when the lines are optically thick. And the fact that it just falls out naturally does suggest that this is some relation to what's going on. Simulations of isolated prestellar cores with the standard assumptions about the importance of the magnetic field and the structure have basically no relation whatsoever to actual observations of prestellar cores. It could be due to the we've been underestimating magnetic field strength for a while, or it could just be a fundamental limitation in modeling isolated objects when these objects are not isolated in the slightest in reality. And I think that's probably something that people need to move away from, given that it's completely feasible with modern computers to just form these things from clouds and study them then. So with that, I will stop talking.
Thank you very much, Felix. Very interesting results. We have plenty of time for questions. If you have any question, you can unmute your microphone and ask this question if you want. Or I can read the question for you.
I guess we covered everything then.
Well, I have a question. At the beginning, when you mentioned the turbulent cloud model, I was wondering if you mentioned molecules like 13CO, HCN, N2H+, and I was wondering if a molecule like SEO, tracing shocks, could help in the analysis.
That is something that I've always been meaning to look at. The problem is the shock part, as you said. So at least my understanding of the chemistry is that SiO gets sort of knocked off grain surfaces as it passes through shocks in molecular clouds. And while you can model that, it's not entirely clear how you do it in the framework I've set up, where you follow the individual particles. So you'd have to have some definition basically of when has that blob of gas been shocked, which I'm sure you could do. It's just that I haven't got any obvious sense of how to do it. So it would definitely be interesting to look at what the shock traces are doing, but actually modeling what the shock traces are doing is the sticking point at the moment.
Okay, thank you. And I was wondering also if you include feedback in your modeling. I mean, the presence of the outflow maybe generated by the presence of the magnetic field in prestellar cores.
No, this is, again, a kind of fundamental sticking point is that we stop the simulations the point that you form a star, because after that it all gets very complicated. I know that people have, I mean, there are obviously simulations which include feedback, so it would be possible to include it, but I haven't worked on that myself yet, and I'm not entirely sure how to go about including it. So in principle, if it's captured by the hydrodynamics, then it can be captured by the chemistry as well. But it's definitely something I'd be interested in looking at in the future. But at the moment, I'm again sticking to nice 10 Kelvin gas, which hasn't been disturbed by anything, just for pure simplicity, basically.
And a little bit related with that, what do you think will be the role of cosmic rays in the dynamical evolution of clouds?
In the dynamical parts?
Well, I don't know, in the evolution of molecular clouds in general. I mean, apart from the cosmic rays, I know some people like I mean, it's not my field, but some people is claiming now that can have an important role in the evolution of clouds themselves.
So cosmic rays are included basically just as a standard cosmic ionization rate in the chemistry.
Okay.
They're not included specifically in the dynamics, other than the fact that the gas temperature is sort of, at some sense, set by the cosmic ray, right? So there's no direct.
I guess it will affect basically the dissociation or ionization, excitation of H2, basically, no, and that will affect the
No, yes. So I've not looked at changing the cosmic ionization rate, but yes, if we did, then I would expect massive.
It's just you have a feeling of the importance. So what do you think about the importance?
I think, well, so everything I've done has been assuming a kind of the standard 10 to the minus 17 ionization per second or something. I've been planning on looking at something more central moleculars only, but at the moment that seems to be causing some issues with the chemical convergence. So I would expect massive differences to basically all the chemistry if you did do that. I'm currently need to find what bug is crashing the code to do it. I think other people have looked much more intensely at this, maybe not with sort of actual cloud scale models, but in terms of the chemical effects, using 1D things or something.
Okay. And what related with your last point, like, what do you think would be the most important effect of the external influence on the molecular cloud? Because your molecular cloud, in fact, I mean, your simulation reproduced very well the overall properties of the molecular clouds. It's just a small course. So do you think actually the environment have an important effect on the properties of the molecular clouds? It's just, I mean, a nice question because it's not my field. I'm just curious.
Yes, well, so if by environment, do you mean the actual sort of
environment? I mean, I don't know, spiral allowance, the vertical pressure, the galactic environment.
Galactic scale. I kind of assumed it would, but based on the fact that the starting off with an isolated sphere of turbulent gas seems to end up looking more or less like real clouds. I'm not actually sure it does. So
okay.
The difference between that and the cloud collisions, I think, is that's less to do with environment, I guess, and more, are you squashing things together? So again, it would be interesting to take the kind of galaxy scale simulations people have of, actually forming molecular clouds self-consistently out of galaxies. And I kind of originally assumed you'd have to do that because I wasn't expecting the cloud models to work, but they kind of did, which suggests you can get away with it, and they doesn't have it. But again, I don't know this for I'm speculating that it doesn't matter too much. And if it does, that would be trouble for me.
Okay, thank you. Thanks a lot. Thanks for the talk. I enjoyed it.
Thank you.
Yeah, I think there are no more questions. So thank you very much, Felix, for the very interesting talk, for joining us.
Yeah, thank you.
And thank you, everybody, for joining us. Thank you.
Thank you. Bye.
Thank you.